What exactly is generative AI, and how does its architecture work? Today, we decode the hidden mechanics behind large language models. We are currently experiencing a fundamental paradigm shift in computer science and enterprise infrastructure architecture across the globe. For decades, the relationship between humans and machines was dictated by analytical and strictly deterministic artificial intelligence models. We provided the strict rules and the structured data, and the machine simply executed the predetermined mathematical output. Today, that entire architecture has been inverted. To understand generative AI practically, we must first establish the correct taxonomy. Artificial intelligence is the overarching academic discipline. Within it lies machine learning, where systems autonomously learn from vast datasets. Deeper still is deep learning, which utilizes artificial neural networks with multiple layers to process highly complex data patterns. Generative AI is a highly specialized, advanced subset of deep learning, and it operates entirely differently from legacy systems. Traditional machine learning models are discriminative. They classify or predict based on existing data, like flagging an email as spam. Generative models, however, are probabilistic. They do not merely classify data, they understand the underlying distribution of the training data. This deep understanding allows them to generate entirely new, synthesized outputs that share the exact statistical properties as the original dataset. We are no longer simply querying a static database. We are interacting with a system capable of semantic synthesis. The catalyst for this massive leap in capability was the introduction of the transformer architecture in the year 2017. Before transformers, models processed data sequentially. This severely limited their ability to retain context over long sequences of complex information. The transformer architecture solved this processing bottleneck through a revolutionary mathematical concept known as the attention mechanism. In simple terms, the attention mechanism allows the artificial model to assign different weights of importance to different words. It does this for every word in a sequence, regardless of their physical distance from one another in the provided text. The system evaluates the relational context of every single word against every other word simultaneously, mapping a complex geometric web. This is why when we interact with a large language model, we must realize we are not actually inputting words. We are inputting tokens. A token can be a full word, a subword, or even just a single character of text. The model utilizes billions, sometimes trillions, of parameters, which are essentially the synaptic weights learned during its extensive training phase. It uses these parameters to calculate the strict mathematical probability of the next logical token in a sequence of text. It is an incredibly sophisticated engine of statistical prediction, grounded in high-dimensional geometry rather than human linguistic rules. Moving from theory to practical application, what does this actually mean for modern digital enterprise infrastructure and corporate leadership? It means we must immediately stop treating large language models as if they were traditional web search engines. They are not retrieving pre-written information from a static repository or a hard drive. They are dynamic cognitive reasoning engines, because they generate responses based on probabilistic mathematical pathways. They excel at synthesis, translation, and advanced pattern recognition. They can connect ideas across completely disparate domains of human knowledge in seconds, accelerating enterprise research exponentially. However, this probabilistic nature introduces specific and critical vulnerabilities that every IT professional must thoroughly understand and mitigate. The most notable vulnerability is the widely documented phenomenon known academically and operationally as an AI hallucination. Because the model is strictly designed to predict the most statistically likely next token, it prioritizes linguistic fluency over factual accuracy. It can generate highly plausible, incredibly confident, yet entirely factually incorrect statements if it lacks sufficient training data. It will also inevitably hallucinate if the user fails to provide adequate context within the initial prompt given to the system. Understanding this fundamental limitation is absolutely critical for deploying these models in a secure, professional enterprise environment. It underscores the strict necessity of human-in-the-loop verification processes for any high-stakes business or technical operation. It also demands the implementation of strict operational guardrails and parameters when integrating these generative models into corporate workflows. We cannot blindly trust the output without verifying the underlying logic and the data sources used to generate the response. The architecture of intelligence is no longer about programming the right answers. It is about engineering the right cognitive frameworks. The models are only as effective as the architecture surrounding them, which requires a fundamental shift in IT strategy. Instead of asking what the software can do for us, we must ask how we can mathematically guide the software's reasoning. This is where advanced techniques like fine-tuning and retrieval-augmented generation begin to play a monumental role in modern business. We will cover those specific architectural frameworks in depth in the next video of this Enterprise Masterclass series. But first, we must solidify our understanding of the generative foundation we have thoroughly established here today. You now understand the transition from deterministic execution to probabilistic generation, powered by complex attention mechanisms and transformer models. You recognize that LLMs are not databases, but statistical prediction engines operating within incredibly vast, high-dimensional vector space. This foundational knowledge is the absolute prerequisite for mastering the technology and avoiding costly implementation errors in the field. In our next masterclass session, we will bridge the gap between this theoretical architecture and practical, secure enterprise deployment. We will examine exactly how to integrate these cognitive models into your existing operational frameworks safely and efficiently. We will explore how to ground the Model-E's probabilistic outputs in your own proprietary corporate data to prevent costly hallucinations. We will also look at the rigorous cost-benefit analysis of training your own model versus utilizing an established enterprise API. The AI vanguard is not composed of those who merely use the tools, but those who understand how to architect them. To support today's lecture and your ongoing professional development, I have prepared a comprehensive technical guide for your review. This companion documentation details the specific parameters, taxonomies, and architectural models we have discussed in this current session. It is strictly designed to be shared with your IT departments and engineering teams to perfectly align your corporate understanding. It provides the rigorous academic framework necessary to lead digital transformation initiatives within your respective highly competitive industries. You can access this full technical documentation immediately in the professional GitHub repository linked in the video description below. Review the materials thoroughly, prepare your architectural questions, and ensure your team understands this critical baseline generative technology. By mastering these foundations today, you position your organization to leverage AI as a definitive strategic advantage tomorrow. The future of enterprise technology belongs to those who build the architecture, not just those who query the interface. Subscribe to continue the AI Masterclass, download the GitHub technical guide below, and join the vanguard. Thank you for your time.